In the late 1700s, the early natural historians of the Enlightenment were still strongly influenced by dogmas. Early scholars such as Giovanni Arduino tried to shoehorn all the rocks that he could see into a simplistic sequence, with primary rocks, granites, and metamorphic rocks like schist supposedly formed when the Earth was created. These were covered by secondary rocks, which were layers of sedimentary beds, which were often folded or deformed. Above these were the loosely consolidated sediments and sedimentary rocks known as tertiary beds. These simplistic ideas of the rock record could be entertained, as long as you didn't go into the real world and look at real rocks too closely. But most geologists at the time did not travel very far or check their ideas against outcrops. Instead, they forced the limited rock exposures of Northern Europe into their previously accepted dogmas. This scheme, that all the rocks supposedly were formed by water, became known as Neptunism, after the Roman god of the sea, Neptune. The Neptunists argued that even lava flows were once laid down in water. Their opponents, however, argued that lava flows were once formed by hot, molten rock, not from water, and so they were called Plutonists after Pluto, the Roman god of the hot volcanic underworld. Among the most prominent Neptunists was German naturalist Abraham Gottlob Werner. He was a professor of mineralogy at the Friedberg Mining Academy. Werner was said to be a spellbinding lecturer and a powerful personality who made devoted converts of nearly anyone who heard him speak. His concepts were among the most popular in Europe, primarily because of the force of his arguments and personality, and were not based on close examinations of an outcrop over a wide area. His disciples were found in almost all the major European universities, including the University of Edinburgh, where Robert Jameson was a convinced Neptunist, who also became the arch-rival of James Hutton. Even the great poet and naturalist Goethe was a convinced Neptunist. In the fourth act of Faust, there is a dialogue between a Neptunist and a Plutonist, wherein Mephistopheles is clearly a spokesperson for the evil Plutonist viewpoint. You might ask yourself, how could anyone think the volcanic rock was formed in water? Remember, chemistry was in its infancy at the time, so no one knew about the heat and pressure needed to melt rocks. Few Europeans had ever even seen a lava flow. We are used to watching videos of glowing hot molten lava flowing in active volcanoes, but in Hutton's day, few Europeans traveled far from their hometowns, and none had seen a volcano erupt unless they happened to be in southern Italy at a time when Vesuvius happened to be erupting. And those volcanoes mainly produce ash and not lava flows. Yet, as James Hutton thought about his grand scheme of mountains being uplifted and eroded away, he became convinced that rocks, such as granites and basalt that formed lava flows, were produced by hot molten rocks known as magma, and not laid down in water. But there was no active volcano anywhere in Northern Europe, and Hutton had never seen a lava flow move across the landscape. In the absence of this evidence, Hutton looked for places where granitic rocks or basalts had melted away or intruded through pre-existing rocks and baked the rocks surrounding them with their enormous heat. Hutton got his first clue when he noticed that the gravels in the River Tilt, flowing south out of the north of Edinburgh, were full of both granitic pebbles and older metamorphic rocks. From this, he knew that both kind of rocks must be exposed in the riverbed, and he might possibly see where one contacted the other. In 1785, he rode up the valley of the Tilt and stayed overnight at a forest lodge. The next day, he found what he had been looking for. Veins of brick red granite cutting through the older metamorphic rocks and baking the zones around them. Here was proof that granites were once molten magmas, not formed in water. Here was proof that granites were once molten magmas, not formed in water. Not only that, but the granites must be younger than the metamorphic rock, and therefore not all rocks had been formed during the original creation. But Hutton needed something even more convincing. Lava flows that were intruded through layered sediments that had been formed in water. Finally, on the southwestern slopes of the Scottish mountains, he found what he was looking for. The intrusions of basaltic lava that melted their way through layered sediments and even deformed them in the process. This spot is so famous that it is now known as Hutton's Section, and geology classes visit it on a regular basis. Hutton and his chemist friends also had much better insight into the chemistry of rocks than anyone else at the time. Hutton knew what minerals, such as salts, formed by chemical precipitation from water, look like. And he could see that in magmas were not formed in water. When Hutton moved to Edinburgh, he worked with Black, who shared his love of chemistry, a key tool to understanding the effect of heat on rock. In 1792, Hutton and his friends performed an experiment in which he melted a piece of basalt at a temperature between 800 and 1200 degrees Celsius, and it recrystallized into basalt again when it was cooled slowly. This was one of the first examples of experimentation in geology and proved what molten rocks would look like in nature. Having read accounts of hot springs of volcanoes, but never having visited them, Hutton was convinced that the Earth was hot and molten in the center, powered by what he called the Earth's Great Heat Engine. In his words, the volcano was not created to scare superstitious minds and plunge them into fits of devotion. It should be seen as the vent of a furnace. His ideas were further confirmed by coal seams that had been baked by lava that intruded through them. He believed that this heat engine was responsible for the uplift and building of mountains, which then became sediments that were washed to the sea. These processes went on in an endless cycle of uplift, erosion, deposition, and uplift again. All of these ideas were part of a broad overview of a dynamic Earth that was incredibly old and constantly remade and recycled. Not a young Earth that had remained essentially unchanged since its creation some few thousand years ago. With the publication of his essays and his book, The Theory of Earth, in 1795, Hutton put forth his concepts for the rest of the world to see. Yet, Hutton's ideas were not immediately accepted. Partly because his writings were so difficult to read and understand, when Hutton died in 1797, he was still not widely appreciated. Although in 1802, his protege, John Playfair, published illustrations of the Huttonian theory of Earth, which made the case clearer and was more widely read. It would take another generation for such revolutionary ideas to win acceptance in the geological community. This happened thanks to a young man named Charles Lyell. Born in 1797, the year that Hutton died. Originally trained in the law to become a barrister, he soon became bored and instead pursued the young field of geology as a hobby. He traveled widely over Europe, witnessing many different geological phenomena with the uniformitarian eyes of Hutton. Eventually, Lyell wrote his masterpiece, Principles of Geology, published in 3 volumes from 1830 to 1833. The book is written essentially as a legal paper, mustering all the observations he had gathered from his travels and his readings. He used his skills as a lawyer to argue a decisive case for the uniformitarian view of the Earth. Like any good lawyer, he used any tactics necessary to discredit his opponents, the catastrophists, while presenting overwhelming evidence for his own case. He confirmed Hutton's ideas of the Earth's great heat engine with multiple accounts of volcanic eruptions and hot springs, especially in southern Italy, where Vesuvius is located. Within a few years, the last of the old line catastrophists and Neptunists had died, given up, and geology became a modern science. Thanks for watching. If you like geology, here's a video about the natural history of New York City, and you can write in the comments below a topic you think I should cover next.